Okay, this is lecture 16. I'm going to do a second example of a discrete time Markov chain. So just to remind you from the previous couple times, the discrete time Markov chain is a discrete time stochastic process which actually satisfies this Markov property. So remember what the Markov property is. It's basically a memoryless property where it says that the next time only depends upon the current state. So what happens in the future only depends upon what happens in the present. Okay, so example 2. We have an office building that gives out free hot drinks to employees. The options are either tea or coffee. Each day, 70% of the people who drank tea yesterday choose to drink tea again today. So apparently people like tea. Also, 20% of those who drank coffee yesterday switched to tea. So some of those who drank coffee yesterday switched to tea. Some of them just keep drinking their coffee, and likewise, if you're drinking tea, you're likely to stay with tea again. So if one day there are 120 people drinking tea and 80 people drinking coffee, how many people will be drinking tea 1 day later, 2 days later, 1 week later? And we basically want to plot the trend in Matlab for 2 weeks. And then a second question is, what if initially instead of the 120 people drinking tea and 80 people drinking coffee, we had it switch? So what if we initially had 80 people drinking tea and 120 people drinking coffee? So in this case, how many people are going to be drinking tea 1 day later, 2 days, 1 week? And again, plot the trend. And then look at the trend and see why do you get the results that you get. Okay, so we're going to do this example just like we did the example in the previous lecture. We're going to draw our transition diagram. So in order to draw the transition diagram, we first have to figure out what our states are. In this case, we have two states. We have T and C is what we're going to label them. T, basically you drink tea. C are those who drink coffee. So what else do we know? We know that each day 70% of the people who drank tea yesterday choose to stay and drink tea again today. And then we also know that 20% of those who drank coffee yesterday end up switching to tea. So how do we draw the transition diagram? We start just like we did before when we were talking in the previous example. We start with our two states. We have T and C. What do we know? We know that 70% of the people who drank tea yesterday choose to stay drinking tea, which means how many people go over from the tea to the coffee? Well, if 70% people drink tea, then 30% drink coffee the next day. Okay, we also know that 20% of those who drank coffee switch to tea. So here we have this switch from coffee to tea. But if you're already drinking coffee, then you're more than likely to stay with coffee with a probability of 80%. Okay, so what's the transition matrix? Remember what we did last time. We have the current state as our columns and the next state as our rows. And so what's the probability that if you're drinking tea, you go to tea the next time? That's 70%. What's the probability that if you're drinking tea, you switch to coffee? Tea to coffee, that's 30%. Okay, now if you start at coffee, what's the probability you're going to switch to tea? So here, coffee to tea, that's 20%. And coffee to coffee, that's 80%. So double check, make sure that you've done everything correctly. The columns should sum to 1, and they do, so you've done things, at least on the surface, it looks like you've done things correctly. Okay, so here's what we have. We have that our initial state is 120 people drinking tea and 80 people drinking coffee. So how do we find state 1? We multiply our initial state by our probability transition matrix. Here's our transition matrix. So 1 day later, we have 100 people drinking tea and 102 people drinking coffee. So now for day 2, we do this again. We multiply our previous state by our probability transition matrix, or remember what we can also do is take p squared times S0. And again, we're going to get 90 and 110 2 days later. Let's go out to 1 week. 1 week later would be p to the 7th. So we're talking about 7 days later. So we're going to take this to the 7th, multiply it by our initial state, and we have this. So we don't want to do this by hand all the time, so let's look, and basically we take that code that we had previously, the plot state code, and we're just going to modify it slightly. So here we're going to have plot state t, which just means it's our example 2 problem. Again, our input is going to be how many days in this case, not months, days in this case you want to consider. So this just closes any previous figures that we had. Here is our probability transition matrix. Remember, we have to change this from what we had initially in that first code. So we're going to change it, modify it to what we have for example 2. We're going to initialize our state. So our 2 columns and our first 2 rows in our first column is going to be our initial state 120 and 80. Let's print it out and keep a table of things. So again, we're going to go and multiply our p to the I times our initial state. We're going to print out what we do, and then let's plot the trend. Okay, so if we do this with the tea and the coffee, here we have 14 days, so this is our 2 weeks, because we really don't want to do 2 weeks by hand. So notice what is happening here. So if you notice, it looks like it's approaching a steady state. If you look at the graph, again, it's approaching a steady state. So it looks like after so long, assuming all the transition matrix stay the same and they don't really change with time, then what is expected to happen is that eventually you're going to reach the steady state in which you have about 120 people drinking coffee, and you end up having 80 people drinking tea, and that's about what it's going to stay on average. Okay, so now what did we have? So this was the part that we already answered. We said we looked at 1 day, 2 days, 1 week, and we plotted the trend in Matlab for 2 weeks. So now this is the second part of the question, is what if instead we switched and we had 80 and 120? What's going to happen? So if we have 80 and 120 and we plot the trend for 2 weeks, notice these numbers don't change. Why don't they change? So the question is why do these stay the same regardless of where I'm at? So go back and look at what we had before. Remember this trend where we started with 120 people drinking tea and 80 people drinking coffee? Well, when we had this, then we got this trend, and remember what we said this was? Steady state had 120 people drinking coffee and 80 people drinking tea. So if we start with that, if we start with 80 people drinking tea and 120 people drinking coffee, then what are we going to do? Well, we're just going to stay there because that's our steady state. What's it mean to be a steady state? It means it's not going to change. It's steady across time. So it started at the steady state, so it's going to stay there for all time. Okay, so this is a very short lecture. I just wanted to give you another example of a discrete time Markov chain, how to set up the transition probability transition matrices, how to set up the transition diagrams, and how to use Matlab to actually do this. Okay, so next time we're going to talk about assignment 4. Assignment 4 is going to be a group assignment, so I'll talk about that in the next lecture.